Now, I don't necessarily want this to take too long, so if you feel like when we're actually working on it, you're at a stuck point, you know, you can take a break from it and if I'm not available, or you can call me over. But here we are going to go ahead and skip to chapter 9. Right? So we're jumping from chapter 6 to chapter 9. Sounds like that's kind of insane, but not really, because I'm only interested in one thing from chapter 9. Okay? And the one thing I am interested in is, is the tree rotations. So first we're going to talk about why rotations are a thing. And the answer is it's because we need them for self-balancing search trees. So, what is the average case runtime for insertion and deletion or any operation in a tree? What's the average case? Yes. Log n, log base 2 of n in a binary search tree, because ideally every time we go down a link, we cut out half the search space. Worst case scenario is what, though? O of n, right? And we'll see a couple of examples of that in a second. So, but the idea here is that if our tree becomes unbalanced, which means that and a tree is unbalanced if your subtrees differ in height by more than 1, right? If your subtree's height differ in more than 1. That's and that process and that definition is recursive too. Okay, so if they're unbalanced, there's a risk that basically you get into an O of n runtime. Now, fortunately, the way a self-balancing tree works is that with AVL trees and red-black trees, is that you start out with a balanced tree, and then if you add an item or remove an item and it becomes unbalanced, then they have different ways of detecting that and reshuffling the trees reshuffling the items in it using something called a rotation. And so in add and removal, that takes log n time, right? And what happens is that these rotations, they take at most log n operations to do, right? So you have log n to do your operation, log n to rebalance in the worst case, that's log n plus log n, and that's still O of log n, right? So, so there's two different types of self-balancing trees that are very common, the red-black tree and the AVL tree. I learned about the AVL tree when I was doing my undergrad, and I just simply prefer to, and just simply for time constraints, I'm not really going over them, or I'm not torturing you with them. Sometimes you're asked to implement them as a homework assignment, but not this semester, okay? AVL is named after the authors, as you'll see in a second. So we're just going to briefly go over them and those ideas, but mainly what I'm interested in is this idea of, right, which I've already went over with basically, if they become unbalanced, then the tree, then it becomes off of log n time. Well, the reason it's log n is that if it's balanced right, then there's n levels. If there's n items, there would be log n levels, and so basically the item you're looking for is at most at the lowest level. So these are some examples you might see of an unbalanced tree with the tree that I've written. Right? This is where if I added the numbers 1 through 9 in order, right, you'd get a tree that looks like this. It's more of a linked list, right? A realistic thing might be like this, where if I inserted the words, the quick brown fox jumps over the lazy dog, right? Now notice that it is not a straight line, but it's not going to give you log n time because each of those times we get a branch off, it immediately stops. Every time we make a left or right, it doesn't cut our search space in half. It's essentially a linked list with a couple of weird, hanger-ons, So that doesn't really give us the time we need. So what we use is something called rotation to do that, and it's an interesting operation. We're specifically going to focus on a right rotation today. Right rotation, there's a right rotation and a left rotation, and the reason I'm going to focus on right because all you have to do to program a left is to take a right rotation, replace all the rights with lefts and all the lefts with rights, right? And then boom, you've got yourself a left rotation. So what a right rotation and a left rotation does is that it rebalances your subtree's heights. It takes so here, notice that on the left, 20 subtree is the roots subtree over here, it has a height of 2, right? 1, 2. And the height of this subtree is 1. If we do a right rotation, which I'll go over in a second, then we end up with both sides having a height of 2. Right? It rebalances and redistributes the stuff. Now, the way this works, and because I'll be saying English, but you're not necessarily going to understand it, and I'm sorry. The way it works is that the root grabs its left child's right child and takes it and adopts it as its left child. Meanwhile, the old left child adopts the root as its right child. Like I said, that was all English words, and they all had basically 4th grade reading level words in there, so, yet it was still incomprehensible. This is because it's one of those things that's way easier seen drawn than done. But what happens over here, right, is that notice that 20 is the root. And when we rotate around 20, we rotate around a specific node. It can be either a tree or a subtree, right? What it does is that it takes its left child's right child as its own left child. Okay? And then basically it moves down while 10 moves up and adopts the root as its right child. So the algorithm for this is as follows, which is what we're going to implement today. It's 4 lines of code, by the way. We start with root, right? We grab root.left and we basically say root.left, your temp, right? Okay? So we store our left child. We grab our left child's right child. Okay? Everybody see how that arrow moved from pointing to here to pointing to here, right? And now temp says my right child is root. Okay? And then we say temp is the root. And so now look at the way the tree looks. 10 is the root. Its left child is 5. Its right child is 20. And 5's right child is 7, right? And notice that basically despite it looking really weird, all the stuff to the left of the root is less than the root. All the stuff that's to the right of the root is greater than the root. So this rotation preserves the BST property. And this is just simply looking at it at the way we would normally want to look at it. Now, our PowerPoint images they're actually okay at this. But fortunately, we don't have to rely just on the PowerPoint for this. There's an entire Wikipedia page, which is actually very beautiful. It's almost as though computer scientists really like, Wikipedia and these collaborative processes. So, yay, they use Greek here because that makes it seem nice and friendly. Okay. No, instead this is the way right rotation and left rotation basically do this, right? Notice the nodes are all labeled, right? Right, when this happens, what happens is that basically P moves up and P essentially tosses B to Q, right? They essentially are tossing, right? If we do right rotations and left rotations, right, they're essentially tossing this guy back and forth, right? So for a right rotation, essentially our left child tosses us their right child, and then we become their child. Or in animated form, let's take a look. So this is a right rotation right over there. Now interesting, this beta subtree, the reason this works and maintains balance is because this is greater than A. So now since it's moving it's still to the right of A. But it's also less than B. But throughout this entire operation, it is always to the left of B. Right? Notice that it's all that this subtree is always to the left of B and it's always to the right of A. That's why it will preserve balance, and nothing about these alpha and whatever this is changes. All right. It's Greek to me. All right. So let's go ahead and go over another nice drawn example. Okay. Right. We want to do a right rotation where pivot is going to become the root. So the first step, we find the pivot, which is called temp and the other things, which is my root's left child. We say root's left child is pivot's right child. Pivot's right child is the root. And now we just basically grab pivot and kind of just shake it out so that that basically all the nodes just dangle from it correctly, you know? All right. So that's a tree rotation. That's how various schemes keep various self-balancing schemes keep this get this working. So what are those schemes anyway? Well, one is the AVL tree, developed in 1962, named after these guys. It's named after these guys. Adelson, Velsky, Landis. I probably butchered that. Okay, but it's named after their initials. What it keeps track of the differences in the heights to each subtree, right? So as we add nodes, and you can go through this on your own time if you want to. You're never going to be tested on it in this class, right? We've got, I figure our time is best spent elsewhere, right? We have to make sacrifices somewhere. And basically it has all these schemes for keeping track of what the heights should be. And what's interesting is, this is the slide I wanted to get to, is that there's two different, it figures out there's 4 different scenarios for a tree being unbalanced. There's left-left, there's left-right, there's right-right, and then there's right-left. And then they each have a solution. Oh, rotate right around the parent, or rotate left around the child, then rotate right around the parent. Or then, oh, if it's right-right, then rotate left, right? So it has these, it says if you detect one of these 4 situations, right, because we identified them now, we can detect them, you can solve it with a rotation, with a series of rotations, okay? So that's how that one, and that it just does that by keeping track of the heights of that. Again, I'm not really going to go into that. I was just giving the general idea that basically the idea here is that it detects if it's unbalanced, and then it will just do these rotations, okay? Now, yep, see a lot of stuff there. So red-black trees, on the other hand, they are named because we add one more attribute to the nodes. They can be either red or they can be black, right? And then we have these 4 rules that always must be maintained. A node's either red or black, right? The root is always black. A red node always has black children. We consider any null references to be black. And then we calculate the height of the tree based off of how many black nodes there are. So the path to any leaf in this tree has the same number of black nodes. So here, 2, 2, 2, right? Or 3 if you want to count the nulls. Okay, and so what we do is that whenever we insert stuff and we find something is violated like that, we have a way of changing it. So we are like, okay, we can recolor things, and if the recoloring doesn't work, then we have to do a rotation, right? So it will recolor things as needed, and then it will rotate. Now it lets the tree get actually a bit unbalanced, I believe. It lets it get more unbalanced than the definition of balance allows. It allows a difference of height. It allows a difference in height of 2 rather than 1. And then at that point it will rebalance. So it allows things to get a bit more unbalanced, but it will still be log n, but it's still log n insertion. So, but basically it just checks what invariant will be violated, and then it has, depending on what invariant we're working with, we have a way of solving that. So those are red-black trees. The only other tree I'd like to mention are these guys, which show up occasionally, which right, we've been dealing with binary trees, and instead we've got something called we've got this thing called a 2-3 tree. Named so because nodes can have either 2 children or 3 children, okay? And the idea here is that, how does this work? Well, if you've got 2 children, it works exactly the way it does in a binary tree, right? Everything less than is to the left, everything greater than is to the right. So if you've got 2, so anybody kind of have a guess of how this works if you have 3 children? Right, we've got 11 and 15. Any guesses of how this is working? Yes?
Yeah, you
Sorry? What? I missed what you said. Oh, sorry. You can either can go.
All right, so left side is less than both 11 and 15. Middle is greater than 11, less than 15.
Mm-hmm.
Right is greater than both.
Yep. So what it is basically left and right work basically. So left, it's less than. So you have two values in here, x and y. Left and x is less than y. Everything to the left is less than your first number. Everything to the right is greater than your second number. And everything in the middle is in between. Now, the reason why do this? It allows you to basically speed up your searches because now you can because if it's like complete, if you got it, ideally if you get, well, it's one reason. It's just another way for keeping it balanced. But also, like, if everything's like a 3 node, then you could like ostensibly, cut everything. Instead of having it, you could third your search space with a single search, which is pretty cool. And of course, there's 2, 3, 4 trees, which work exactly as you imagine and are annoying. But so there, yes.
So that node has like 2 values?
Yeah, this node has 7 and 15 as a value.
And then do you just code a node with one value that has the same value twice?
There's different ways to do it. I mean, or you can just leave one empty.
But then I was like, yeah,
And you have to code that in. There's different ways to do it. I've never actually coded up one myself, unfortunately, but they exist, and I've been taught they exist, and they're just fun to know about. All right, so that's just a different way of handling things. So anyway, that's chapter 9 in a nutshell. So for today's exercise, and if you spend more than 15 minutes on this, just move on. Okay, I want you to implement a right rotation, right? It's worth 5 points as a quiz grade. There's a drop box available for it, and it does close at the end of the night. So be sure to get it in. But here, use the Wikipedia page to do it. Implement a right rotation. Now, fortunately, you aren't completely going into this blind. If you go to my GitHub, which you can find on the Canvas site, and go to Pages, if you go under the destruct folder for data structures and go into the trees folder, you have access to my binary tree file, which is the one I've been modifying over here, right? And you can use that, and I built a binary tree in here. Now, my print line works in a very interesting way with indentation, with basically the more indented it is, the deeper in the tree it is. So basically, like, you'll have the root on the first indentation, and then the next indentation level will be the left child and then the right child, and so on and so forth. The next indentation level will have their children and so on and so forth. But the way you want, so let me just show you, because this was a bit of a stumbling block for the other students to get this done in a good amount of time. This is the way your right rotation method should look, right? This is the head. This is your declaration for it. So public, static, or sorry, it shouldn't be static. It should be public, because it's an instance method. Node E, right rotate, and it'll take in the node you want to the root you want to rotate around. Node E root. Okay. So it's going to take in, and what it's going to return is the new root of the tree, right? It's going to return the pivot, essentially, the guy who's the new root. And so the way you will test that is by going over here, right? You'll print the tree over here. Then we'll do the right rotation, and then they'll print it again. And the way you do your right rotation, and this was a stumbling block for a lot of students, and it shouldn't, you know what? Why should it be? Tree.root is equal to tree.right rotate tree.root. So if 0 ends up as the root and all the nodes are still present, right, 5 will be the original root. If 0 ends up as the root and all the nodes are still present, then you've done it correctly and you can just upload it. Okay? Make sense to everybody? Great.